Okay, it says recording. Okay. I'd like to start right on time. Okay. So, good morning. It's Wednesday. You know, when it's Wednesday, the weekend isn't far away. We know we can get there. Right? Let's just talk about the things that are coming up before the weekend. Okay. We have homework due tomorrow night. We have office hours for me this afternoon from 2 to 4. You just go to Blackboard Collaborate. And if I don't happen to be there hanging out, just shoot me a quick email and say, hey, could you meet me in your office? But I'll probably be there hanging out. But I might be talking to somebody too. So again, if you just shoot me an email, or if you're in Blackboard Collaborate, and hopefully I'm there hanging out, just unmute your mic and say, hey, Dr. Trees, I'm here. Okay. Tomorrow afternoon from 2 to 4 are also office hours. You have tutor tonight from 6 to 8. If you want to talk to me at other times, you can reach out via email. If you want to literally talk to me face to face, we can set up a time to meet on Collaborate or Google Meet. Okay. So that's for your homework coming up Thursday night. Then, like last Friday, this Friday we'll have a quiz. It will be the same format as last Friday. That's why I did that one last Friday and made it kind of a practice run, bonus points, okay? So that you get used to how you do it, because it's going to be done the same way. But this time's not bonus, all right? It's going to be based on one of the homework problems from Thursday night that I will take and massage a little bit. The massaging is to see if you understand the problem and are not just memorizing steps to solve it, because that's not learning, okay? But as I said, it'll be the same rules, same time frame as the quiz last Friday, just a different problem, okay? Okay, one thing I want to point out, because I don't think I've mentioned it yet, and some of you might have noticed, the class slides that I'm showing you in our class time, I am uploading those to Blackboard. They are there under class content. So you can see those, all right? For today, for example, I've uploaded those already. So you can see those so that you don't feel like you have to frantically write down something that's printed on a slide, but can focus your note-taking on things that we work through together, like when we do a practice problem on the board together. That's worth writing in your notes, because that's modeling for you how to solve the Wiley Plus problems, right? Definitely worth taking notes on and studying. Question?
So this is a question like pertaining to the homework. So I looked at the homework, and the first problem is almost the same exact problem with different numbers as the fourth problem on homework that was due on Monday.
It's the same exact problem?
It's different numbers. I just wanted to hear the answer.
Oh, well, I guess that one got added extra then. I don't know if I can change it now, but if you've solved that other one already, it'll be easy, won't it? Yeah, it wasn't really my intention.
So for the video lecture for this class today, do you want us to like differentiate between, because under the definitions you had said like instantaneous velocity and magnitude and stuff, but then for in a three-dimensional version, could we call it like 3D position because it's in a third dimension?
It's a three-dimensional position.
And a three-dimensional like displacement.
Okay, so I just wanted you to be aware that the slides that you see in a class session are already there on Blackboard for you to refer to, okay? All right, one other quick note comment I want to make, and then I want to get started with the content for today. I want to say a word to try to make you feel a little bit better about lab, because I think you feel a bit stressed about lab. First, let me point out, let me try to allay your fears. Everybody feels stressed for that first experiment. Not that one we did last week. That was a toy experiment, all right? The one this week is the first real experiment. There's a lot of new ideas that get thrown at you, aren't there? Takes a while to get used to. Here's the good news. There really aren't any more new ideas. Every experiment we do from now on is going to use these same ideas and pretty much the same generic pattern. First, you will gather some data. That will be measuring length, mass, and time. Those are the three kinds of things you'll measure. Okay? Even though it might be a different experiment, right? It's still length, mass, and time. You'll gather data, then you'll analyze data and draw some conclusions. You'll do that in every experiment. The analyzing will almost always involve making a table, but it will also almost involve making one or more graphs. And for each graph, doing a curve fit and using the curve fit parameters to get the value of something, okay? So we will be doing the same thing in every experiment. So it's not like with each experiment you do, there's all kinds of new definitions and new terms to learn. It's really the same terms, just you get more and more and more practice with them. So what you discover is with each successive experiment, you start to get a little bit more familiar with terms like absolute uncertainty or standard deviation of the mean, and all that kind of stuff. And although it feels a little unsettling at first, bit by bit, it will start to feel more familiar to you, okay? But it always feels a little unsettling at first. You just do your best, you gather your data, you do your measurements the best you can, and then you follow the instructions in the lab manual. If it says make this kind of graph, make sure that's the graph you made. Do this kind of fit, make sure that's the kind of fit you do. Then you're basically doing what you're supposed to be doing, okay? So it will bit by bit start to get better. One of the things, I'll give a little bit of the spoiler away for this experiment. Most of the time we're going to do linear fits, not polynomial fits like the cubic one. And if you were struggling with the graphs this week, you might start to see why. Higher order fits are very notoriously difficult to get good parameters, fit parameters for. Very difficult to get good fit parameters. But not so much so for linear. There you tend to get much more reliable fit parameters. Okay? Okay, so don't be panicking. Just say, okay, this is stuff I'm going to be getting better at. In the meantime, I will do my best to do what the lab manual asks me to do. Okay? Then don't forget to save your lab report as a single PDF that you upload for your group with you and your partner, okay? Okay, so I just wanted to try to make you feel a little bit better about lab. Now what I want to do is we're going to finish chapter 3 and start chapter 4 today. And what I want to do to finish chapter 3 is do one more Wiley Plus type example problem that involves working with vectors. And because I'm going to need all this board, I'm not going to bring the screen down. And I know it doesn't project that terribly well onto the whiteboard, so I'll read it to you. But please note, this slide is on Blackboard. So please don't waste your time or energy trying to write all those words down, okay? Just write in your notes, example 3.2. And then write what we do as our work. Does that make sense? So it says, hard to read, I know. We have an expedition in the Antarctic and we have an emergency. Here's what's happened. Scout team number 1 has completed 2 displacements from base camp when one member of that team falls gravely ill. The first displacement was D1 arrow equals 0.750 kilometers. And then there's that example of what was in the video lecture called a unit vector. I hat, you call that. It has magnitude equal to 1, that thing, and it merely points in the plus x direction. So this vector is given to us in what's called unit vector notation, this displacement, D1. The second displacement we're going to label D2. This one we're given in a magnitude and direction form. It has a magnitude of 1.5 kilometers and was directed 30 degrees above the plus x axis. So we were given a magnitude and a direction for that one. Now, that's what Scout Team 1 did, those 2 displacements. The doctor is needed. The doctor was with Scout Team 2 when the news comes that the doctor is needed. Scout Team 2 has undergone 1 displacement from base camp. We're going to label that D3. It has a magnitude of 2 kilometers and is directed 50 degrees above the negative x-axis. So they're telling me magnitude and direction for that one. Here comes the question. What single displacement that we'll call D4 will allow the doctor to reach the location of Scout Team 1? Because that's where the sick person is. We are to give our answer for D4 both in magnitude and direction form, as well as in what's called unit vector form. Okay? All right. I'm going to clear this. We'll remind ourselves of the numbers as we work our way through because I need the space to write on the board. Okay, so let's start with a sketch, yes? Because there are a lot of words in that problem, and let's convert them to a picture. Apparently, we are to think of an XY coordinate system. So you're looking down from above on the region of the Antarctic where we are. And perhaps it's fitting then that we're using a whiteboard. Let's go ahead and put the base camp at the origin, right? Doesn't that seem like a reasonable choice? You don't have to do it that way, but that I think is probably the most common choice. That's where we'll put the base camp. Now I've got these various displacements that have happened. D1, D2, and D3. We're going to sketch them, okay? On our picture with arrows. I'll remind you what the first one was, D1. Because we were given that one in unit vector notation. 0.750 kilometers, I hat. So if I'm going to draw an arrow representing D1, it starts at base camp. That's where they started. Which way do I draw the arrow pointing? Plus X, okay? So let's start with an arrow starting at the base camp and going out some distance in the plus X direction. And label it D1 arrow. There's the first displacement. I'm just sketching, so I'm not going to worry about getting a scale exactly right, but I certainly know the direction. Then they complete a second displacement, D2. That was given to me as a magnitude of 1.50 kilometers and directed 30 degrees above the plus X axis. Since the second displacement immediately follows the first, we'll pick up right there at the tip of D1. But how should I draw the D2 arrow? Any thoughts? At an angle above the x-axis. Technically, it would be a 30-degree angle. All right? Any thoughts on how long? Hint. This one is a magnitude of 0.75 kilometers. D2 has a magnitude of 1.5 kilometers. What's that? Twice as long, right? So now we'll draw an arrow twice as long going upward. It'll just a sketch would help. Even just doing this much is going to be very helpful. This then is where they are, right? Team 1, Scout Team 1 is right there. When the person got sick, okay? Scout Team 2, remember, is where the doctor is. Scout Team 2 also started out at base camp, and they completed a displacement that the problem calls D3. It has a magnitude of 2 kilometers and is directed 50 degrees above the negative x-axis. And that's a little bit of a different way to tell us direction. So how should I draw D3? It starts at base camp, right? Which way does it point? Mm-hmm. Right? Because if that's the plus x-axis, that's the negative x-axis, right? To the left of the origin, 50 degrees above that puts you up in here into quadrant 2. And it's 2 kilometers long, which means it's even longer than D2, isn't it? I don't know, something roughly like that. D3. Let's label a couple of angles. This angle right here is 30 degrees, right? This angle right here, 50 degrees. This then right here is where Team 2 is. At that location in the XY plane. That's where the doctor is. So guess what? The doctor has to do one more displacement, right? Because the doctor has to get to where the sick person is. Sick person is there. The doctor is there. You should be able to sketch. Go ahead and draw it there in your own notes real quick. What is the displacement vector that the doctor needs to undergo now? You want to tell me how to draw it? And nice and loud, please, because I'm somewhat deaf. To there. Draw an arrow, like that, right? Yep, draw an arrow. I'm sorry, I can't hear you. Sorry, what is that? We're going to call it D. Problem said to call it D. Okay, D4, right? The problem said to label it D4. That's really just a personal choice, but if the problem said call it that, we better stick to it. That's the thing we have to find, isn't it? The one I just drew with the orange marker, so we'll put a question mark by it. That's the thing I have to find. All right? Both in unit vector notation and magnitude angle notation. But my sketch already tells me quite a bit about it, this D4. Just look at the sketch. Tell me the sign of its x component. Is its x component positive or negative? It's positive. Because this vector, I can tell, that it points to the right and down. Yes? So the x component must be to the right, and the y component must be down. The x component to the right is positive. But the y component points down. That's the negative y direction. So the y component is going to be negative. I can tell that just from my sketch, so that I can check my math when I get my numbers. Okay. All right, so now we're down to the big question. How are we going to actually compute D4? Mm-hmm.
You break down the vectors into their components.
Mm-hmm.
Then you're gonna have your this is the way I would do it. You have your x components, and so you want to take the absolute value of those x components. Then that'll have the total distance that you need. Then you also want to have your y component of D3 minus the y component of D2. And that's going to be your components on D4.
Okay, that's getting me there. It's getting me there. But what I want to notice first, though, is there's a kind of an underlying big idea here that's going to guide us to getting D4. It has to do with the fact that there was the beginning at the base camp and the ending at that point, right? That's what has happened. These two together, D1 and D2, got us to that point, yes? So the total of these two displacement vectors is this vector, right? Add those two vectors, D1 and D2, and you get the one I just drew in green. The sum of those two vectors is the net. What has to be true about the total displacement for the doctor? The doctor went up here and then over there. No? Where did the doctor start? Base camp. Where did the doctor end up? Right there. What can you tell me about the total displacement of the doctor compared to the green arrow I just drew, which was the total displacement for that first team? They're the same. Yes? D1 plus D2 is the green arrow, and D3 plus D4 is the green arrow, right? Because D1 and D2 are head to tail, and the green goes from the tail of the first to the head of the second. That's vector addition. But D3 and D4 are head to tail as well, aren't they? And the green arrow goes from the tail of the first to the head of the second. So what you have to see is that D1 arrow plus D2 arrow is equal to D3 arrow plus D4 arrow. And I think the picture helps you come to that conclusion, but you have to state this idea clearly. That is your guiding principle for solving this problem. That D1 plus D2 must equal D3 plus D4, but be careful, it's vector addition, not the scalar addition you learned in first grade. Vector addition. And we must use vector algebra. Now, there's still only one unknown, D4 vector. So let's solve that equation for it the way we would any algebraic equation with symbols. Isolate the quantity we want to solve for. So if we get D4 by itself on one side, D4 arrow, that's D1 arrow plus D2 arrow minus D3 arrow. You see what I did? I just used algebra and isolated the D4 vector. Now, here's the next thing I recommend you do. With those arrows, you're reminding yourself, oh, these are vectors that can have, in this case, an X component in principle and a Y component. So this really stands for two separate equations. One for X components only, and another for Y components only. So what you really need to do next is write this all again, where every D has an X subscript. I'll put a comma. D4X equals D1X plus D2X minus D3X. Once you're writing the components, by the way, you don't put the arrow on top anymore, because that's not the whole vector. That's just the X components. And then a separate one for the Y components. D4Y equals D1Y plus D2Y minus D3Y. You see what I've done here? Those are the equations we're going to use. And then we're going to find D4X and D4Y. Now, to do this correctly, the next things we have to do is for each of the three vectors we already know, D1, D2, and D3, write down their X and Y components. I'll remind you what D1 was. It was written like this: 0.750 kilometers times I hat. And since this is a two-dimensional problem, if you want, you can also think of another term added on, plus 0 kilometers times J hat. Unit vector notation is what this is called because it uses these little symbols called the unit vectors. I hat's the unit vector that points in the plus X direction. J hat is the name for the unit vector that points in the plus Y direction. The reason we like unit vector notation is all you have to do is look at the things multiplying the respective unit vectors and you've got the components. In other words, D1X is whatever multiplies I hat, 0.750 kilometers. D1Y is whatever multiplies J hat, 0 kilometers. That's not bad. Now let's work with D2 because we need to find its X and Y components, right? So I can put them in their various slots in my equations over here. All right, here's what I recommend you do. Hey, if you're busy, if you're focusing on finding the X and Y scalar components of D2, just draw a new picture with just D2. Focus like a laser beam on what you're trying to get. Right now, you're trying to get the components of D2. Redraw D2. Might as well slide its tail over to the origin, help you visualize. There it is. That angle is 30 degrees, right? I just slid its tail over to the origin. Sketch the X and Y components. That's good practice for you. You should be able to draw the component triangle for that. Okay? And you should be able to do it about as fast as about 10 seconds. Okay. Notice D2 points up and to the right, so it must have one component to the right and one component up. So if I drop a perpendicular, there, just draw a regular arrow is D2X, the one to the right, and a regular arrow up is D2Y. And now we're finding scalar components of a vector, which we've talked about already and has been in earlier video lectures, right? But we need to be able to do that. So how do we calculate D2X and D2Y? We know the angle, 30 degrees there. Also note, we know the magnitude of D2. That's the vector there along, that's along the hypotenuse. Its magnitude is 1.5 kilometers. So I've got a right triangle where I know the length of the hypotenuse and that angle. So I ought to be able to use trig to find this leg and then this leg, or that leg and then that leg. Doesn't matter what order. Let's do the X component, D2X. Look at the triangle. The triangle is very important. It's this leg I'm finding. It is adjacent to the 30-degree angle, and I know the hypotenuse. So I think I'm going to use the cosine. Cosine of 30 is adjacent over hypotenuse. So cosine 30 is D2X over D2 magnitude. Rearrange that and solve for D2X. It's D2 magnitude times the cosine of 30 degrees. Hypotenuse times cosine of the angle. So 1.50 kilometers times the cosine of 30. I will tell you what you get, just so you can see what the number is, 1.30 kilometers. And you found D2X. You see how you're going to find D2Y? What formula would you write right here for calculating D2Y? Okay. Magnitude D2 times sine of 30. So 1.5 kilometers times the sine of 30. Sine of 30 is 1/2. Half of 1.5 kilometers is 0.75 kilometers. Okay, we found the x and y components of D2. All right, well, I still need to do the same thing for D3. So let's draw yet a new picture for D3. And this picture will contain just D3 and my coordinate system. I'm going to draw it kind of like this, anticipating how I'm going to draw D3. D3, it's already got its tail at the origin. That's good. Just points up into quadrant 2 at 50 degrees there. So let's sketch it again. Basically like that, D3. This angle is 50 degrees. Okay, sketch the components on a component triangle. Note that D3 points to the left and up. So the x component must point to the left. There's D3x, and the y component must point up. There's D3y. And I'm just going to use that right triangle to find D3x and D3y. In other words, I'm going to use the 50-degree angle. That's how I'm going to do it. Because I tend to use acute angles, i.e. angles that are not larger than 90. But that's just my preference. Okay. All right, let's find the x component. Let's use the 50-degree angle. The hypotenuse would be the magnitude of D3. I know what that is, 2 kilometers. Anybody want to tell me how to write the expression for D3x? Warning, it's a little bit tricky. You want to? Yeah, you want to say?
Can you repeat the question?
So the question is, tell me what to write for the calculate D3x. What do I write here? Based on how you saw me write the components for D2.
Magnitude of D3 multiplied by minus cos 50.
All right, so I'll put the minus in the front, but minus magnitude D3 cosine of 50 degrees. Everybody, let's be clear on where that came from, because we have to be able to get that. The minus sign, with this approach, using the little right triangle and the 50-degree angle, the minus sign must be inserted by us by hand from our knowledge that the x component points to the left, which is the negative direction. So you have to put the negative in by hand, but the rest is just trig. Length of hypotenuse times the cosine of 50, because D3x is adjacent to the 50-degree angle. So that's negative 2 kilometers. That's the magnitude of D3 times the cosine of 50 degrees. So you're getting a negative x component, and you get negative 1.29 kilometers. That negative sign is absolutely vital. Okay, somebody tell me what to write for D3y. Yeah, Alex.
The absolute value of D3.
Absolute value of D3 times the sine of 50. Do I put a minus sign in front? No. All right. D3y points up, doesn't it? That's the positive y direction. No negative sign for D3y. That's also vitally important. So 2 kilometers times the sine of 50 degrees, that turns out to be 1.53 kilometers. Okay, now I've got expressions for D1x, D1y, D2x, D2y, D3x, D3y, all very carefully calculated with appropriate positive or negative sign, 3 sig figs. Don't round any lower, fewer sig figs, or you're probably going to have too much rounding error. And I even put units on all of them. Now I'm ready to go to this equation and then this equation. I can find D4x with this one and D4y with this one. But I have to use those equations exactly as you see them. I cannot change the game now in the middle. The rule for calculating D4x using vector algebra is take D1x plus D2x minus D3x. So D1x, 0.75 kilometers. That's a decimal. Plus D2x, make sure we get the correct number, 1.3 kilometers, minus, parentheses, D3x, negative 1.29 kilometers. Look at that very carefully. This is the level of care that you need to solve these kinds of problems. See how easy it would be to make a sign mistake? You must have good focus, concentration. Now, when you get all that out, the answer is positive 3.34 kilometers, positive. Well, we already knew from our sketch, didn't we, that D4 pointed to the right and down. Therefore, D4x is to the right. That's positive. And I can tell just by looking at it that this x component is pretty darn big, right? So my answer for D4x at least seems reasonable. Now we have to get D4y by taking D1y, 0, plus D2y, 0.750 kilometers, minus D3y, positive 1.53 kilometers. And do that in your calculator very carefully, and you get negative 0.780 kilometers. Negative. I knew I had to get that because the y component is down, which is the negative direction. So I can immediately now give you D4 in what's called unit vector notation. It's easy once you have the two scalar components. Just take the scalar component, the x scalar component, that's positive 3.34 kilometers, and multiply it by an I hat. And then add to that whatever you have for the y scalar component, negative 0.780 kilometers, and multiply it by a j hat. I mean, you are literally simply writing the value of D4x and then multiplying it by an I hat, then plus, then writing the value of D4y and multiplying it by a j hat. And you have expressed that vector in what's called unit vector notation. Okay, so the doctor's displacement D4 must have an x component to the right of 3.34 kilometers and a y component down of 0.78 kilometers. Okay, now, for the sake of time, I'm going to just talk us through the next part. There's a little bit more to do here. But the heart of this problem is solved. We have found that second displacement of team 2, D4. But we expressed it in unit vector notation. The problem also asks, give us D4 as a magnitude and a direction. Okay? So if I tell you the vector right like this in what's called unit vector notation, that means you know the x and y components. They're just the numbers there and there. So who can tell me, using that information, how I would find just the magnitude part of D4? Exactly. It's the square root of D4x squared plus D4y squared. Because you're just finding the length of the hypotenuse of this vector right here. Because now what I could do if I wanted to is sketch its x and y components there and there. Okay, well, you can put those numbers in, square them, add them, take the square root. You will get 3.43 kilometers. You've given then the magnitude of D4. But we also have to give the direction. I recommend you draw yet one more picture, X and Y axes, in which you sketch the D4 one more time, but put it here at the origin so that it's all by itself. The D4 points down and to the right. D4, sorry, that's not easy to see. And then there's the X component, there's D4X, and there's D4Y. I need to find that angle right there, theta. Thoughts on how to get that?
You can use sine of theta, take it as the inverse sine.
So what numbers would you be using with the inverse of sine?
So sine of theta equals D4 over, or D4x over D4.
No, not quite. If you want to use sine, D4y, or the magnitude of D4. Take the inverse sine of that. Could you use cosine? What would you use then? Theta equals the inverse cosine of what would be in the of.
The x component over the magnitude.
Everybody understand what I'm asking? I
Yeah.
have one person answering here, but it's not, okay, so I'm getting some more hands. I don't make sure everybody understands this.
Can you hear me?
You have multiple options, right? If you want to use cosine theta, that's adjacent over hypotenuse, that'd be D4x over the magnitude of D4. So I take the inverse cosine of D4x over the magnitude of D4. What if I was bound and determined to use the tangent function?
You take the
What
ratio.
numbers would I use?
Professor, can you hear me?
Yeah, Colin.
Oh, you can.
Yes, I can, Salim. I'm having Colin answer.
Oh, okay.
Yeah, opposite over adjacent, D4y over D4x. So you can do it a number of ways, yes? But you got to show your work if it's a quiz or a test so I can see what you're doing, yes? You can't just write theta equals without showing me what you did. Okay? So however you wish to do it, you may do it, but you need to show me your steps. I will tell you what the answer is. Is it a positive angle or a negative angle? It's negative because it's measured clockwise, isn't it? The angle is negative 13.1 degrees. So that and that could also be your answer, magnitude and direction. Okay? Okay, Wiley plus problems from chapter 3, they're coming. We have to be able to do vector algebra. Now, let's move on and start talking about chapter 4. Oh, Wiley plus. Sometimes Wiley plus, I just want to strangle you. Okay, I'm going to open up a new slide here, just a second. Now, I sent you the video lecture for the first section of chapter 4. So that's where I laid out all the ideas that we need. There we go, that. Now, let me open my PowerPoint slide and turn this on. And now I will bring the screen down, make it easier to see. So first I start with the learning objectives for the first section of chapter 4, which you can also see on the slides that I've uploaded to Blackboard, because it's these very slides. And there are a number of learning objectives that we want to be able to do, to complete. First, with regard to position and displacement, and then with regard to average velocity and instantaneous velocity. Like draw 2-dimensional and 3-dimensional position vectors for a particle, indicating the components along the axes of the coordinate system. On a coordinate system, determine the direction and magnitude of a particle's position vector from its components, and vice versa. And apply the relationship between a particle's displacement vector and its initial and final position vectors, which we're going to start practicing with. And then average and instantaneous velocity. We have to remember that velocity is a vector. It has both magnitude, direction, and also components. We have to be able to draw 2- and 3-dimensional velocity vectors for a particle, showing the components on a coordinate system. We have to be able to find the average velocity vector, given the initial and final position vectors and the amount of time. And then given the position vector as a function of time, determine the instantaneous velocity. Those are the things we have to be able to do. You already, hopefully, watched the video lecture for this material, where I talked in quite some detail about position and displacement, and average velocity and instantaneous velocity in 2 and 3 dimensions. So let's just start practicing right away, okay? All right, so we're gonna practice, this pen is dying, kinematics, we're still studying motion, in 2 dimensions. What I'm gonna show you, to start with, is a Wiley Plus animation. Let me get to that. Okay, there it is. What are we seeing here? We're looking down from above on an XY coordinate system. X going to the right in meters, Y going up in meters. Maybe you're floating up overhead in a balloon or a helicopter. And in this flat region of space, maybe it's a flat field, there's something moving. I don't know, maybe it's a squirrel. And the actual path is the curve in black, at least for some amount of time, right? From there on up and along like that. That's the path the particle is taking. And we're going to practice describing the motion of this particle using kinematic quantities, okay? All right, now I'm going to read to you and go through with you some of the things we're going to do, at least we're going to start with. Okay, first, there's a kind of a starting time we're interested in. But just to kind of give us a little bit more something to think about, the starting time, T1 is not 0, it's 2 seconds. That, I will just tell you, is right here. That's where the squirrel is at the time T1 equal to 2 seconds. So you see that blue arrow right there? What do you think that represents? What do I mean? We've got various kinematic quantities. We've got position, displacement, average velocity, instantaneous velocity, at least so far. What do you think this blue arrow represents right here? Mm-hmm. Sorry? Initial position, exactly. It is the position vector. How do I know that? Because by definition, the position vector for a particle points from the origin out to where the particle is at that time, okay? Anybody remember from the lecture, or if you read in the book, What's the symbol your book uses for a position vector? R. New notation now, isn't it? R, in fact, R with an arrow on top. So if I hover over that blue arrow here on my laptop, see if I can get it. There it is. You have to look carefully, but it says R1 arrow. The initial position vector. You know what I want us to do here? It's going to be an approximation, but that's okay. I want us to write down the expression for R1 arrow in unit vector notation. Meaning, I want the x component of R1 times I hat plus the y component of R1 times j hat. And I want us to estimate those numbers that go there and there. Admittedly, it will just be an estimate because all you've got is what you see there. Okay? Okay, let's do that one first. So there's R1. All right, so imagine the little component triangle. You're trying to imagine that in your head? The little right triangle with R1 as the hypotenuse? Then roughly about that would be the x component, wouldn't it? Just imagine that going straight down to the x-axis. You see what that number, let's say it hits that tick mark there. 5, right? I think it's 5. That's a pretty good approximation, I think. So 5 meters I hat. Thoughts about the y component of R1? Now imagine either going straight up like that, how far do you go, right? Approximate. Thought? Yeah, it's just a little more than 20, exactly, right? It's just a little more than 20. The number I'm going to use is 21, but 22 would have been fine. But I just want to be consistent. We'll do one more, then we'll pause for today. Now, I'm going to write down the formula for a position vector R2. R2 is the position vector at a later time, T2, that we get to pick with that slider up there. And right now, T2 is set at 6 seconds. Fine. Then that's where the squirrel is. And there it is, right there, the red dot. The red squirrel, obviously. Okay. So that's the position vector R2, right there. Let's write it down in unit vector notation. So some number times I hat plus some number times j hat. Well, you would play the same game as you did with R1. Imagine the component triangle. How far out do you go this way? That'd be the x component. How far up do you go this way? That would be the y component. I'll just tell you what the numbers are. 21 meters for the x component. Right? X component's bigger here. And 5 meters for the y component. One more. Anybody know from the lecture what that symbol means? It's the change in vector R. R is position, so it's change in position. What's the name for that? It's the displacement, okay? That would be R2 vector minus R1 vector. It's easy to subtract vectors when they're in unit vector notation. Just take the difference in their x's times I hat, delta x times I hat, plus the difference in their y's times j hat. Delta y times j hat. You see, just subtract the x's. Take 21 minus 5. Yes, that's 16, right? 16 meters I hat. Plus, now delta y. Now make sure you take R2 minus R1. So 5 minus 21. Negative 16 meters j hat. That's the displacement of the squirrel between T1 and T2 in unit vector notation. I contend it's one of the arrows. Any thoughts which one it is in the drawing? The delta R? It's the green arrow. Because it has a positive x component and a negative y component. They're roughly equal, right? The components point to the right and down. There I can even show them. Okay? There's the displacement. Notice it just points from the initial position to the final position. Okay, there's a little more with this I want to do, but this is a good place to pause, so we'll pick this up on Friday.